Welcome to this video on Module 4, High-Pressure Pipeline Logistics. We will explore fluid phase behavior, supercritical hydraulics, impurity metallurgy, and fracture control models for carbon dioxide transport. In this first part, we examine the fundamental thermodynamics and phase behavior, essential for understanding how carbon dioxide acts within pipeline systems. Supercritical and dense phase fluids offer significant hydraulic advantages by combining liquid-like density with gas-like viscosity. This minimizes friction and optimizes throughput, provided we manage the system as a single phase. Understanding critical state thresholds is vital. Pure carbon dioxide reaches its critical state at 31.1 degrees Celsius and 7.38 megapascals. Operators typically maintain pressures between 80 and 150 bars to keep the fluid stable. Two-phase flow introduces serious hazards. If pressure drops below saturation, cavitation and slug flow can occur, causing severe mechanical damage. Furthermore, two-phase dynamics can trigger hydraulic choking, limiting your transport capacity. Moving to Part 2, we will discuss the impacts of impurities on corrosion and the hydraulics of our pipeline systems. Trace contaminants are a major concern. When CO2 mixes with water, it forms carbonic acid, causing localized corrosion. The presence of SOx and NOx further intensifies this, creating stronger acids that accelerate material degradation. This table outlines key impurity limits. Maintaining low levels of water, H2S, and other gases is essential to prevent operational issues like corrosion, stress cracking, and increased energy requirements. Impurities also shift solubility limits. Non-condensable gases can trigger water condensation unexpectedly, while cool temperatures may cause dissolved water and methane to crystallize, potentially causing blockages. Part 3 focuses on metallurgy and the specific steel chemistry required for high-pressure CO2 transport. Selecting the right steel is crucial. Industry standards like API 5, LX65, and X70 are preferred for their balance of strength and toughness. Tight control over microstructure and specialized sour service properties help mitigate cracking and corrosion. Charpy V-notch impact testing is a standard method to ensure steel ductility. It helps identify transition temperatures and ensures the material can absorb enough energy to prevent brittle fractures. Drop weight tear testing, or DWTT, is another vital validation tool. By using larger specimens, it simulates full-scale fractures to ensure the pipeline material can withstand extreme impact loads. In Part 4, we address the critical challenge of running ductile fractures in pipeline systems. A running ductile fracture is a major threat. Because gas compression stores significant energy, a crack can travel rapidly. Strategies such as specifying high-toughness steel are necessary to arrest these fractures. In this section, we analyze decompression wave dynamics. When a structural breach occurs, pressure drops rapidly, initiating an expansion wave. Controlling this wave is the foundation of dense phase safety, as unlike natural gas, supercritical carbon dioxide pauses at a high-pressure plateau that can continuously fuel crack propagation. Carbon dioxide has a high Joule-Thomson coefficient, which causes severe cooling during expansion. A leak can drop temperatures toward -78.5 degrees Celsius, forming dry ice. This thermal shock can embrittle standard carbon steels, significantly increasing the risk of structural failure. The Battelle Two-Curve model is used to predict fracture arrest. It compares the decompression wave velocity to the steel's fracture propagation velocity. If the decompression wave moves faster than the crack tip, the pressure driving the crack is lost, and the fracture is arrested. Now we will explore crack arresters and the integrated safety systems designed to protect pipeline integrity. When steel manufacturing limits are reached, mechanical arresters are deployed. Heavy wall rings physically block cracks, while composite wraps, such as carbon fiber sleeves, provide high modulus constraint to prevent the pipe from opening or flattening. Advanced monitoring technologies are essential. Distributed acoustic sensing uses fiber optics to detect leaks in real time, while RTTM modeling provides precise location data. Furthermore, automated emergency valves allow for immediate isolation of damaged sections. Part 6 covers the regulatory codes and global standards that govern the safe design and operation of CO2 transport infrastructure. Regulatory compliance is mandatory. Pipeline design must strictly adhere to established safety codes to ensure integrity and reliability across various operational environments. Transporting dense phase CO2 requires higher Charpy V-notch toughness than standard hydrocarbons to prevent running ductile fractures, particularly when impurities are present. In the final section, we review flow assurance and the dynamics that influence booster station and pipeline routing. Booster stations must be positioned to maintain net positive suction head above critical limits, preventing pump cavitation. Additionally, Routing over undulating terrain requires careful simulation of high points to avoid low-pressure vapor pockets. Controlled blowdown logistics are vital. Venting high-pressure segments must be carefully scheduled. If done too rapidly, the Joule-Thomson effect can drop steel temperatures below brittle limits. Customized nozzles are often used to manage these expansions. Transient hydraulic events like liquid hammer can occur during rapid valve closures, potentially exceeding design pressures. Similarly, negative pressure waves can induce vapor column separation, causing gas cavities to collapse and damage the pipeline. Subsea pipelines face unique geotechnical challenges, including thermal upheaval buckling from hot compressed fluids, vortex-induced vibrations from ocean currents, and potential structural collapse from extreme external hydrostatic pressure at depth. Thank you for joining this session on high-pressure pipeline infrastructure. We have covered the critical safety, hydraulic, and metallurgical aspects of dense-phase CO2 transport. Please feel free to review any section as needed. If you are interested in further collaboration, including consulting engagements, research proposals, or professional technical training, please reach out via the contact details provided on this screen.